was kind of the lesson, one important lesson from the lecture is that even if you don't succeed in what you attempt to do, some wonderful things can happen. We saw the first sort of absolutely spectacular failure by Strassen, who realized that the standard algorithm for multiplying matrices is not the best one. And I did not mention it this morning, but think about just how important that is. Most people, when they use mathematics, most of what they use is linear algebra. And most operations, maybe it should not be linear algebra, but that's the way the world is today. And almost all operations of linear algebra essentially amount to multiplying matrices. If you take an inverse of a matrix to solve a system of equations, or if you do just about anything, you're going to have to multiply matrices. So although there's a beautiful theoretical interest in this result, there's also a very practical question, especially if we can multiply matrices of some reasonable size, say 1,000 by 1,000, quicker than standard. This would have a real impact in the real world. And somehow this question later we saw was related to algebraic geometry in several levels, because sometimes the best, quote, algorithms are not really algorithms, but sequences of algorithms that converge to what one wants. And that's what we were discussing this morning. So since we ran out of time, I did not give a series overview, which I will do momentarily. And then after that, we're going to cover some fairly routine language to make sure we all understand it. Depending on how familiar you are with these notions, this may take a long time or a short time. Then I'm going to take a little bit of time to talk about the geometry of the matrix multiplication operator from a very elementary point of view, because a lot of what I do, although I will not discuss representation theory in this lecture series because Professor Kwok asked me not to, I will respect that. But I will certainly talk about symmetry. And there's some beautiful symmetry here that everyone should know. And if there's time, I'll begin talking about Strassen's equations. If not, we'll hear about them tomorrow morning. So we talked about this vector space. So A, B, and C are vector spaces. And we'll always be working over complex numbers. And this we can think of as in many roles. These are the bilinear maps from, say, the dual of A cross the dual of B to C, etc. But also as trilinear maps, the dual of A cross the dual of B cross the dual of C to our ground field. And the most important definition was that we had T in this space has rank 1 if T is equal to some little a tensor little b tensor little c, where a is in A, b is in B, c is in C, and the corresponding trilinear map is just a triple alpha, beta, gamma maps to alpha evaluates on A, beta evaluates on B, gamma evaluates on C. And we discussed that. Now, because we'll be interested in geometry, things that do not depend on coordinates, we should keep in mind the changes of bases. So this will denote the invertible linear maps. From A to itself. This is a group, the general linear group. if we fix a reference basis, this is the group of all changes of bases. And if we are going to choose a basis, we should use a good basis. And this group will help us find our good basis. And so the group GLA cross GLB cross GLC acts on this triple tensor product simply by the product of the actions on each of the individual spaces. Now, this set of tensors of rank 1 well, I'm going to work in projective space, so maybe I'll write a bracket for the point in projective space. This is a subset of this projective space. And momentarily, I'll actually show you it's an algebraic variety. I'll show it to you in several ways. And it is a famous algebraic variety, so it gets someone's name attached, Segre. And so I'll write Segre of PA cross PB cross PC, because we'll see actually that it is the, abstractly, it is the product of these three individual projective spaces. I'll return to that in a moment. And this variety is invariant under this group action. If I take a point on this variety, I hit it with an element of this group, I get a new point in this projective space, it'll still be on the variety. In fact, there's an even stronger statement that's true. If I take a point on this variety and I take its orbit under this group, I get exactly this set. So it's called a homogeneous variety. Now, sometimes we'll be dealing with a vector space, a tensor with itself d times. What am I doing? I forgot to give the overview. Nobody stopped me. I started with 2. I should have started with 1. I apologize. Yes, let me do the overview, because that's much more exciting than this. So you need to erase the tape and restart it. That's why I hate being taped, because I do silly things. So these definitions are going to go on for a while, so you want to hear the overview before definition. So the overview of the series, well, because this was where the lecture was supposed to start, and I just, got confused because of this morning. So there's 2 things we're going to talk about. 2 main themes. One is polynomials on spaces of tensors. In particular, this morning we discussed lower bounds on the border rank of this matrix multiplication tensor, and we'll get some lower bounds via polynomials. And the only, or not the only, but the best lower bounds on this border rank, in fact, the only lower bounds on this border rank I'm aware of, all of them have been attained via polynomials. And so we'll bring us up to date on the state of the art in that. Now, we'll also deal with some special equations due to Strassen, and we'll do a detailed study of how good are Strassen's equations. So what I mean by this is Strassen defined a collection of polynomials that gives you a test for border rank of tensors. And if the polynomial evaluates to be non-zero on your tensor, you get a lower bound on its border rank. But what if all Strassen's polynomials vanish on your tensor? Can your tensor be robust? Can your tensor actually be quite complicated nonetheless? And the answer turns out to be, at first, very depressing. The answer is yes. In fact, your tensor can still have close to generic border rank, even when you throw away the obvious things you would like to throw away. And that leads one, even in that very simple situation, to look for new kinds of equations. So, and this leads to new types of equations that are still somewhat conjectural even, but I'd like to present them because I think there's a lot of opportunities for research in this area. And so the first half of this lecture series will be fairly standard material, but I'm hoping to present several open questions that are appropriate for a graduate student to work on. And here, this will be one of those topics, and there'll be a surprising connection with classical problems in linear algebra. So we're doing algebraic geometry of tensors dealing with multilinear maps, but in fact there's a very strong connection with a classical problem involving linear maps. So this may make you happy that you're reduced to something that's been studied extensively, but then you realize that although it's been studied extensively, there are very basic questions even in linear algebra that are not understood. And this somehow this tensor question leads one to one of those open questions in linear algebra. So that's the first main theme of the week, will be polynomials on spaces of tensors. And that subject has been going on for a while. And then the next main topic is something new. It's very new. I'll call it geometry of algorithms. So this morning I gave you two extremely explicit expressions, one for 2x2 matrix multiplication that was found by Strassen, one for 2x2 matrix multiplication with a hole in it that was found by Bini and his co-authors. And both of those algorithms were found essentially by accident. In fact, they were hoping not to find such things. And when you look at them at first sight, they don't look particularly beautiful. They do look like something a machine might have found for you. But what I will show you is, in fact, there's incredible beauty in those algorithms. And once you follow that beauty, there's a hope. And in fact, we'll see that one can generalize those algorithms, not yet as much as we would like to, but somewhat just based on these geometric principles. So this is a completely new subject. And in some sense, we'll get a geometric, well, this is maybe too strong, but derivation, let me put it in quotes. of Strassen, its algorithm, and a geometric explanation, this is not in quotes, of Beanie plus generalizations. Now, at the moment, these generalizations were also found by computer. So let me write Smirnov, who found the generalizations by computer, and they also look ugly at first sight, but they also have very beautiful hidden geometry. So this is a quite exciting, brand new subject. I think this is the first time I'm lecturing on it, which means probably first time anyone's lecturing on it, since it's my co-authors and I. This one is nice because part of this project is with a graduate student at Berkeley, Nick Ryder. Part of it is with a postdoc, Mateusz Michalek. Sorry, I'm getting better. Okay, so that is the overview that I was supposed to begin the lecture with. And now we go back to, definitions. So at some point in your life, you have to do a little boring work. So if we happen to take the tensor product of our vector space with itself d times, then we only have at our disposal one change of basis for all of these. So this is less interesting in that sense because we cannot move things around as much, but we gain something since the things in each of these slots are the same vector space. We can also permute. And both of these groups act on this vector space, and we will exploit that. So, for example, inside this vector space, we have the most important subspace. This is the space of SD invariant vectors, the ones that are invariant when you don't permute them, i.e. these are the symmetric tensors. And this is also the space of homogeneous polynomials of degree d on the dual space of A. So the fact that something is symmetric is the same as it being invariant under permutations. Why, if I have a symmetric multilinear map, can I identify it with a polynomial? Well, so if P is in SD of A, which sits inside a tensor to the D, that says that P is a multilinear map to our base field. And if I feed it the same element, I'm going to ignore this. I can, well, maybe I'll use a symbol P underbar of alpha defined to be this. This is a homogeneous polynomial of degree d. So I just take my multilinear form, I feed it the same thing d times. Now, that's going to be important because algebraic geometry is the study of polynomials. So this is our space of polynomials. There's another important subspace in here, which I'll denote lambda dA, sitting inside a tensor to the d. And these are the skew symmetric tensors. So these are T such that if I switch T of alpha 1, alpha D, this is equal to, if I do a permutation on these indices, I change by the sign of the permutation sigma. So sigma, a permutation. If I permute the order of my things, if the permutation is an even permutation, I get the same answer. If it's an odd permutation, it flips sign. These are the skew symmetric tensors. I'm hoping this is mostly review, but please slow me down if it's not.
It's fine. It's fine.
You're a professor. You told me I should give lectures for graduate students,
Yes.
not professors. If you say, I agree, if you say it's not fine, then there's a problem. But if you say it's fine, it does not mean it's okay. Graduate students, is this okay? Okay, one okay, two okays. Okay, then I can continue. Okay, so if we have a variety, then we define, the ideal of x will be, and let's let a tensor without any symbol be the direct sum of all of these. This turns out to be an algebra because you can multiply, and of course, sim A, you're very familiar, this is just the algebra of polynomials. So this will be the ideal of x just reviewing this morning's notation a little. If I have a point in projective space with brackets, then this is some point in its inverse image in the vector space. I evaluate the polynomial, I get 0. This is the ideal of x. And I don't know at this point how much to say, because maybe you know more than I do about these things. So let's see. So let's give a proof that this Segre is a variety. In the weak sense I defined this morning, just the zero set of a collection of homogeneous polynomials. So we need to find some polynomials whose zero set is exactly the collection of rank 1 tensors. So let's see. Well, let's do an easier thing. Let's consider the Segre of just matrices, rank 1 matrices. Now this is a variety. Why? How do you tell if a matrix has rank 1? Somebody hands you a matrix. They say, does this matrix have rank 1? What do you do to check? Right. This is the zero set of all 2 by 2 minors. And it's an if and only if test. If it's a non-zero matrix, it has rank 1, if and only if it's in the zero set of all 2 by 2 minors, a basic fact from linear algebra. So one of the themes of multilinear algebra is we pretend we understand linear algebra, so we're happy if we can reduce a problem in multilinear algebra to a problem in linear algebra. Now, I could think of, here's a good trick, right? Watch this trick. I can write A tensor B tensor C as A tensor B tensor C. Well, this thing here is a vector space, right? And so I can take the 2 by 2 minors here and I claim, it's very easy to see, that if I have a point here, then all these 2 by 2 minors must be 0. So that gives me some polynomials. Now, I have to say one more thing about tensors. If I write A tensor B tensor C, this is sort of canonically isomorphic, for example, to A tensor C tensor B. And when I want to use this, I'll call this the reordering isomorphism. So in particular, I can also write this space, I could write it as A tensor B tensor C, and then take more 2 by 2 minors. And then I could take more 2 by 2 minors. And I think that's all the tricks I see. So let's see if those 3 sets of equations are enough. Well, if this linear map, so I have T, a linear map from A star to B tensor C is rank 1, that says that T is equal to A tensor X sum X in B tensor C. And similarly here, it'll be some little c tensor some y, here's some little b tensor some z, and then there's just a little bit of bookkeeping that you get a rank 1 tensor. So I leave the rest of the proof as an exercise. Now, it's going to be very important, especially when we study the geometry of algorithms, to study a cousin of the Segre. Well, first there's a young cousin of the Segre, the Veronese variety. So other varieties. We won't need this one so much, but we might as well discuss it. So these are the rank 1 and symmetric. So we could think of these as polynomials that are Dth powers. And I leave it to you to verify that this is the so-called Veronese variety, which is a very nice variety, and people spend lots of time studying it. What will be very important when we study algorithms is the Grossman variety. And this one is a little bit more subtle because it's not points of the Segre variety that happen to be skew symmetric. In fact, no points on the Segre variety happen to be skew symmetric. So if I have an element of A tensor to the D, the smallest, because of skew symmetry, this can be written so what I would want to have is something like this, and I could just skew symmetrize it. Maybe I do this. And now I forced it to be skew symmetric. And a moment's thought will tell you that this is the simplest possible kind of vector in here, inside here. And we'll introduce the notation A1 wedge, A2 wedge, wedge, AD. So this is the notation, I'm just defining. And the Grassmannian is exactly this T such that T is equal to some V1 wedge, wedge, VD, where VJs are elements of A. And you see that those have to be linearly independent. Now, the important thing about the Grassmannian is it has a very nice geometric interpretation as the D-planes through the origin in A. Namely, I take a point, V1 wedge, wedge, VD, and I claim I can associate to it the span of the vectors V1 to VD. This is a one-to-one correspondence. And so this space will play an important role because when we're dealing with algorithms and their geometry, we don't want to deal with these 7 little points or these curves of points. We want to deal with the span of them because the span of them is what will contain our tensor of interest. So if we want to study algorithms geometrically, we'll have to study curves in the Grassmannian. And we'll be talking about that more in future lectures, but it's a very important geometric object. Questions? Okay, I have a few more definitions. This is kind of going to be the most boring lecture, so after this it'll be more fun, but sometimes you just have to establish some vocabulary. Okay, so the next thing I'd like to do is this geometric interpretation of border rank. And fortunately, we saw a little bit of this morning. We saw that a tensor, if this is the set of rank 1 tensors, just schematically, and I have a rank 2 tensor, that means there's 2 rank 1 tensors and a line between them, and my rank 2 tensor sits somewhere on that line. And we also discussed how, in addition to points on secant lines, we picked up points on tangent lines. Well, it's much nicer to discuss some of these questions in their proper generality. So if x is some variety, then we can define the following notion. Well, let's just do that one first. Let's say sigma 2, 0 of x will just be the union, say, from all x1, x2, and x of all of the span of these lines. And this is the union of all points on all secant lines to x. And as we saw this morning, this set is not closed under either the Euclidean or the Zariski topology. And we also saw that we get very lucky that if we take the closure, we get the same thing under Zariski or Euclidean closure. And this will be the variety of secant lines to x. And there's no reason to stop at secant lines. We can study the variety of secant PR minus 1 of x. And this, there's some décalage in the numbering. I apologize, but that's standard now. So sigma 1 of x is equal to x with this notation. So it's the variety of secant PR minus 1s to x. And now our question from this morning could be rephrased. What are equations for the rth secant variety of this triple Segre product? Okay. But now we can study this problem in the particular case of matrix multiplication, or the general situation of algebraic geometry. In fact, the way I ended up studying matrix multiplication was actually because I was studying secant varieties in algebraic geometry. They happen to be the key to the best known approach. Well, I shouldn't say best because it didn't work, but an approach to Hartshorne's conjecture on complete intersections. This was ideas of Fyodor Zak. One could approach that conjecture via a study of secant varieties. It's a very beautiful subject. It also led Zak to study some remarkable things about exceptional groups, particularly the exceptional group E6. But that is not the subject of today's lecture, but it's a very beautiful subject, classically studied in algebraic geometry. So we might as well take advantage of things that are already known in algebraic geometry for our particular question that comes from computer science. Okay. So let's see, is there any other basic stuff I wanted to mention? Do everyone knows definition of dimension and degree of an algebraic variety? It's okay? Okay. And I'm not going to do any representation theory. Yeah, so then let me move on to I think that'll be enough. I think that's enough definitions for one lecture. So we'll add more as we need it. Let's talk about something a little bit more interesting, matrix multiplication and its geometry. So now let me be a little bit more invariant about what matrix multiplication is without coordinates, right? So instead of thinking of space of m by n matrices, I want to think of that as the space of well, let me write it down. Matrices n by m, this is the space of linear maps from Cn to Cm, if you will. And we saw our coordinate free. Maybe let me write this as u and v for what comes next. Coordinate free, we should think of this as u star tensor v. That's what we saw this morning. And so matrix multiplication in coordinates, it eats a u by v matrix. It eats a v by w matrix, and it spits out a u by w matrix. Or if you want to think of it more invariantly, put all three of these spaces on equal footing. It eats a u by v matrix. It eats a v by w matrix. And it eats a w by u matrix. So we have x, y, and z. and it sends it to a number, which is the trace of x, y, z. So I'm going to, this afternoon, to get rid of stars, I'll call this my vector space. Well, the way I'm doing it is A dual. This will be B dual. This will be C dual. So matrix multiplication is some point inside A tensor B tensor C, which I can identify with U star tensor V star tensor W, tensor W star tensor U. So it's some point in that space. What point is it? I claim there's a really sort of God-given point inside that space, and that point is matrix multiplication. Well, as usual, before we try to answer a harder question, let's answer an easier question. Am I speaking too quickly? You are not a graduate student either. But if you said yes, I would have accepted your answer. Am I speaking too quickly? That's a yes. Okay. We will, before answering this question, answer an easier question. So let's look at the space U star tensor U. So this is the linear maps from U to U. Okay, so this is a vector space. Now, of course, like any vector space, there's the zero vector, which is special, but that's not so interesting. But this space is a vector space with extra structure, and it has a very special point inside, or at least a special line. What is that point? What's the most distinguished map from a vector space to itself? Identity map. So inside here, we have the identity map on U. And actually, this is really distinguished, but I'm going to consider the line that it spans. Because this line is invariant under change of bases. No matter, somebody who does not like you picks your basis, and you write down a map as a matrix, this matrix, the matrix representing this map, will always be the identity matrix. It is invariant under changes of bases. It is invariant under choices. So that's answer to easy question. Now we go to a harder question. I claim there's a distinguished point inside this space, just like that space. Well, first of all, the first hint is I can erase parentheses. And the second hint is I can reorder. And now we see there's a very special point in here. It's just the identity map on U, tensor the identity map on V, tensor the identity map on W. And the claim is this is the case. Now, maybe you're not used to thinking of things this way. So let's remember what this makes this identity map so special. It is invariant under change of bases. Well, let's look at the matrix multiplication. Do you prefer a bilinear map or a trilinear map? Professor Kwok says trilinear. No student is going to go against his preference. So we have the map x, y, z maps to the trace of x, y, z. Now, let's say I decide I want to do a change of basis in V, right? Well, if I act by a matrix here, the action on V star is by the inverse matrix. So let's say I have G in GLV, acts on these triple of matrices. Well, this V is going to get multiplied by G on the right. So X goes to X times G. Y is going to get acted on the left by G inverse. And Z, nothing happens because there's no V involved. And so this one maps to trace of X, G, G inverse, Y, Z, which is certainly the same as the trace of X, Y, Z. So it's clear that since this identity map in V is the only thing that has that property, everything is good. And similarly, if I take an H inside GLW, I can multiply here by H, here by H inverse. Nothing changes. And now it gets, well, we don't have to think too much. What if I take some K inside GLU? Well, here it'll get mapped by K inverse, and here by K. So this, ignoring trivialities, this goes to trace of K inverse X, Y, Z, K. But we wanted that. How can we fix the situation? We want that this, we would hope that this is equal to this, no matter what we choose. Well, what do we know about the trace of matrices? We know that the trace of x plus y is equal to the trace of x plus the trace of y, right? We also know that the trace of x times y is equal to the trace of y times x. Well, why don't we call this, well, I shouldn't have used x and y, I'm sorry. Let's call this x tilde, and let's call that y tilde. So this is equal to the trace of k inverse x, y, z. And now we're good. So we see that this point and this point both have the property that they are invariant under the action of this group. I act by this group, neither of these points change. Now that's not enough, unfortunately, to prove that they're the same point, because the line through this and the line through that are the same. But you need to check on your favorite matrix, like the identity matrix. You multiply the identity matrix, or you take this acting on it, you'll get the right answer. So, in fact, this really isn't equal. Questions? No questions? Okay. So, I want to point out, this is the group preserving our favorite point. And then we have this GLA, which is really GL of U star tensor V, but I'm not going to write that. And this group is a subgroup of this in a natural way, or in natural inclusion. This is the group preserving the variety that we're interested in. Well, the variety we're really interested in is its secant varieties, but of course, if the group preserves X, it's going to preserve the secant varieties of X as well. And much of the study of matrix multiplication is a study of these two groups. Okay? The big group of big changes of bases. So if this is n by n matrices, this would be changes of bases, arbitrary change of bases in n squared variables 3 times. And this would be arbitrary changes of bases in n variables 3 times. So this is much smaller than this. It's a subgroup. Am I going too fast now?
No.
Good. So who's a student? I know you're a student. You're a student? Yes, okay. Are you a student? Yes, okay. And I know, yeah. So okay, so you four are allowed to answer when I ask if I'm going too fast. Wait, are you a postdoc or a student?
I'm postdoc.
Ah. Okay. But if you think I'm going too fast, you can tell me. But you cannot tell me that I'm not going too fast. All right. So let me just make one more remark before I get to harder things. Let's take a 3 by 3 matrix. And let's say I take a 2 by 2 minor. Well, let's say this one. Now, if I want to think of this matrix as, say, sitting inside U star tensor V, or maybe just U tensor V, doesn't matter for this discussion, then this 2 by 2 minor has the property that if I swap these two columns, it changes sign. And if I swap these two rows, it changes sign. Well, depending on your choices, these columns are indexed, say, by V, and the rows are indexed by U. And so, in fact, it doesn't matter if I take this 2 by 2 minor or any 2 by 2 minor. It has the property if I swap rows, it changes sign. I swap columns, it changes sign. Yet, nonetheless, it's a polynomial. So what that is saying is that something that's skew symmetric in U and skew symmetric in V sits inside the space of quadratic polynomials. Well, let me put stars here so I don't need them here. And inside here is the 2 by 2 minors. This set of vectors sits inside there. Okay? Does everyone agree that if I have a 2 by 2 minor and I think of it as a polynomial on U tensor V, if I swap the U factors, it changes sign. I swap the V factors, it changes sign. That's exactly what this symbol is about. Okay? The next remark is that if I take the span of this space, I get equality. You can prove that by taking a basis of this space among elements of here, because we know the dimensions of these vector spaces. right? Right, the dimension of A tensor to the D is A to the D. Dimension of sim dA is A plus D minus 1 choose D, and the dimension of lambda dA is A choose D. I'll leave that as an exercise if you've never done it before. And so by just dimension counts, you can get that. So our earlier equations where we took parentheses, we can now understand old equations for the Segre is lambda 2. All right, so now we need a choice. Okay, so we'll have the Segre, yeah. Let's do it, yeah. Segre PA cross PB cross PC inside P of A tensor B tensor C. So we have lambda 2 A dual tensor lambda 2 B tensor C dual sitting inside sim 2 A tensor B tensor C dual plus the permutations. I will not teach representation theory in these lectures, but I will give you hints why you should want to learn it. These are our equations for the Segre. Expressed invariantly. Now, the same trick yields classical equations for sigma r. So the Segre, remember, is sigma 1 of the Segre. And now we're going to get equations for sigma r of the Segre. So anyone care to guess what they should be, either in invariant language or in coordinate language? I'll accept either answer.
Be on the last line.
B, thank you. Yes, professors are allowed to correct me and encouraged to do so. So now we want equations here. And remember here, our trick was A tensor B tensor C equals A tensor B tensor C. That was, we reduced ourselves from multilinear algebra to linear algebra by forgetting structure. Okay, let's start small. Let's try equations for sigma 2. Well, let's try equations for sigma 2, Segre of PA cross PB. So this is the rank less than or equal to 2 matrices. What are the equations for the rank less than or 2? How do you tell if a matrix has rank at most 2? You test all the 3 by 3 minors. The 3 by 3 minors are all 0. It has rank at most 2. So here, we're going to do the same trick. This would be, in this invariant language, 3 by 3 minors. And actually, this has a name of what maybe we'll call flattenings. Because if we were to think of our tensor as a three-dimensional matrix, we're really squashing that down to be a lopsided ordinary matrix. And then we just take the minors, that ordinary matrix. So those are classical equations for secant varieties of Segre varieties. And these give us equations for sigma r PA cross B cross PC up to, well, I guess the max of A, B, and C. Well, if we think about our original problem, let's say for 2 by 2 matrices, Strassen is that M2 is in sigma 7 of the Segre. He actually showed it's in sigma 7, 0. But let's not worry about that. Well, notice this number 7 is greater than 4. And also, 6 is also greater than 4. It's easy with these classical equations that this will not satisfy these classical equations. That's easy exercise. But now we're out of luck. So we need a way to go beyond, for R to go beyond the dimension of the vector space. Next time I will tell you that, but let's just get an idea of how far beyond the dimension of the vector space we might need to go. So maybe, in fact, notice that sigma 7, well, actually let me do that later. 1 second.
How do you want to prove that using flattening that this is not in sigma 4?
Sigma 3, is that? Sigma 3, thank you. Yeah. Even sadder state of affairs, thank you. So let's just do a little dimension count. So this is in general, so we have Segre of PA cross PB cross PC. I didn't prove it for you, but I leave it as an exercise. This really is what its name is. So it has dimension equal to A minus 1 plus B minus 1 plus C minus 1. And if we pick a point on sigma r, we get to pick r points. So expected dimension of sigma r of the Segre will be r times A minus 1 plus B minus 1 plus C minus 1 plus any point on their span, so that's an extra r minus 1. So this is choosing our points, and this is choosing a point in the span. This dimension count may be off if there's shared spaces, but it gives us an upper bound on the dimension. And usually that upper bound is attained. On the other hand, the dimension of P A tensor B tensor C is A, B, C minus 1. Let's set all those numbers equal to m. So this is m cubed minus 1, and this is r times 3m minus 3 plus r minus 1. And we would want to know when is this greater than or equal to that number. So that is, oh boy, I hate doing math on the board. R times 3m plus 1. Oh, but no, sorry. 3m minus 2. Thank you. Help me out. The minus 1's cancel. Greater than or equal to m cubed. R greater than or equal to m cubed over 3m minus 2. So this is some number like m squared over 3, roughly speaking, right? So our equations, the classical equations for r up to m minus 1, as tomorrow's speaker points out, and we have a long way to go. And the state of the art is better than the classical, but it's embarrassingly not that much better. So next time I will present Strassen's equations, which are the first equations beyond the classical. They also are defined by making a retreat from multilinear algebra to linear algebra, but it will be a more sophisticated retreat than what we did for the classical equations. And then I will describe generalizations of Strassen's equations that also come from retreating to linear algebra. And these retreats, these more and more sophisticated retreats, will lead to interesting interaction between classical linear algebra and multilinear algebra. I hope to discuss some non-linear algebra equations if we have time, and that will be about the state of the art, which is, as I said, quite limited. Thank you for your attention.